Hello everyone. First of all, I would like to thanks ICAC, the chairperson and the organizing body of ICAC 2021. Today my topic of presentation is nonlinear super twisting base speed control PMSG-ECS using higher order sliding mode control. And paper ID is 122, author 1 Muhammad Waqas Ayub, author 2 is Zingdong Ma, Department of Engineering, Lancaster University, Lancaster, United Kingdom. The learning objective from this research is to understand the importance of wind energy conversion system ECS and describe the control strategy of wind ECS and understand the concept of maximum power point tracking MPPT and validate the different solutions. The outline of the research article is based on two important parts: wind energy conversion system with PMSG, in which we have wind energy conversion, wind turbine modeling, PMSG modeling, state equation. While the control scheme is we have PID, sliding mode control, feedback linearization, super twisting algorithm, and the comparative analysis of all the techniques. So the wind energy conversion system, we have in the wind turbine based on PMSG, where we have a GB is gearbox, R is rotational encoder, omega H is shaft speed, and omega reference is reference speed, and E represents the reference error and represents the error as shown in figure 1. The numerical modeling of wind energy is based on the wind turbine model. The power is represented in the equation 1, and we can see R is the radius, and V is the speed, and rho is the mass density, and CPR is the power coefficient, and it is presented as. So now the numerical modeling of the based on the PMSG generator we've used is suitable for the offshore wind turbine because the gearless transmission capability, high reliability, ease of control, and low maintenance cost, and it is best for offshore wind system because of broad speed range and greater efficiency and high density of power. The modeling of PMSG in DQ reference frame, we have ID, IQ, and omega S dot, and the above equation, the RS, LD, and LQ and the currents are the stator resistors, ignitions, and currents of the DQ axis respectively, and P presents the pole number, and omega H is the angular rotor speed. Same like omega S denotes shaft angular speed, omega H and phi F is angular speed and flux of permanent magnets. J represents the shaft inertia, and R chopper is chopper resistance, and B1, B2, B3 are constant parameters. Then we have state equation. State equation is basically used here for the simplified form of the constant form parameters, like x1 is equal to ID, x2 IQ, and x3 is omega S. So we can see in the above matrix we have like following constant terms. The proposed control scheme is basically normal form and nonlinear terms we have assessed. The main target is to extract maximum power point power from the system, and this is done by different MPPT control techniques, PID and PI based, SMC, SMC, and super twisting control law. So the sliding mode control scheme is basically as like we have a characterizing surface which is called as switching surface. This switching surface is in terms of errors such as mismatch between two states. The following states are actual and desired. So the switching manifold will be execute this sliding mode alongside with the characterized surface. So at the final we have tracking error, which is like G1 minus G reference. Then the PI based sliding mode control is manifold is and designed as in the following question number 6, in which we have K1 and K2 are the gains. Then super twisting based algorithm is important here. The sliding board produce vibration along switches surface that is not desirable in practical scenario. So we can reduce such vibration and chattering by reachability law. This reachability law is very important, in which we have P1 and P2 are the constant terms. The first terms indicate about chattering reduction, and second terms is indicates a low pass filters which eliminates the vibration. So now we will discuss the simulation results. As we can see, the simulation results, following parameters are set, like the wind speed is 7 meter per second, and tip speed ratio is 7, and maximum coefficient of power is 47.6, and we have time frame of 100 second. So basically the PID and SMC is assessed, then find the proposed STA control scheme is chosen to empower the maximum extraction of the output power. Then the comparison is made between all the techniques with feedback linearization technique. Now, to ensure the maximum power, the ECS operated at its optimal tip speed ratio in all the designed controller cases by controlling the shaft speed. The PMS shaft speed, the PID and feedback linearization behavior chattering with significant steady state error. So all these things will be lower chattering, and compared with the two other techniques can be tracked. So as we can notice that STA is absolutely minimum steady state error as compared to other techniques. So we can see in figure 2 its reference speed tracking of shaft. As zoomed part, we can see its minimum steady state error of STA, the green line, as compared to other. We can see in the others part that figure 3 is basically for the coefficient of power, and we can see again the green line is representing the STA, the minimum steady states error, as compared to others. Finally, the maximum power can be get from STA technique, and the turbine should be run around ORC, and we can see in the zoom part of figure number 4 and figure number 5. Figure number 4 is tip speed ratio, and figure number 5 is tip speed ratios versus torque. And we can see the STA guarantees the smooth ORC tracking, which is turn ensures the reduction and chattering. Finally, the conclusion, this paper is based on the wind turbine ECS is modeled with 3 state variables, which are then transformed into 2 states or normal form model to simplify the system. And then the normal form states are then equipped with PID and SMC for tracking the wind speed in normal wind speed profile for evaluation the controller. During the simulation, it is demonstrated that PID and SMC are showing oscillating behavior chattering with some steady state error that is improved by continuous control component of STA. Then we can finally the future work. It is noted that the research is initial phase of hybrid offshore wind and wave energy. The future work will be based on the artificial bee colony algorithm to improve the maximum power, and I would like to acknowledge my project as to the support of the provided by Lancaster University in terms of PhD studentship, and the research was partially supported by Royal Society of International Exchange 170294, and I would like to thank you everyone for your time, and you can question me. I have few times remaining. Thank you very much for your time. Bye.